All right, so now that we've defined what an infinite series is, we're going to try and evaluate a couple infinite series. In the long run, it'll turn out that most infinite series are too difficult for us to evaluate explicitly, but there are a couple types that are easier to evaluate. One of those types is called a telescoping series. And a telescoping series is named sort of after those toy telescopes that can expand or collapse. And the idea here is that in a telescoping series, a bunch of the series ends up canceling out with itself, and then it's easier to compute. And so that might sound a little strange at first, but I promise it won't be that bad when we actually look at an example. And so let's start with this first example here, where we have the sum from n equals 1 to infinity of e to the 1 over n minus e to the 1 over n plus 1. We already know that the definition of an infinite series is that it is the limit of the partial sums. And so the way we're going to start evaluating this is just by writing out a formula for the nth partial sum. And so again, that's notation for the sum of the first n terms in this series. And so in order to figure out what this is, that means I just have to plug in n equals 1, n equals 2, and so on, up until I get to the nth term in this series. And so that'll look like e to the 1 minus e to the 1/2. That's what happens when I plug in n equals 1 into that term. And then the next term would be e to the 1/2 minus e to the 1/3. And then the next term would be e to the 1/3 minus e to the 1/4. And I'm going to keep on doing this until I have n terms total. And of course, n here is a variable, and so that means that I'm going to have some dot dot dots here overall. And then I'll just have what the nth term would be if I had n expressions total. And so in this case, because I'm starting at 1, the way that I'd get n terms here is if I end with plugging in n. And so in this case, I'll just have exactly what was written already in this series. All right, so now we have an expression for the nth partial sum, but that doesn't look particularly helpful because I know that I want to take the limit of this as n goes to infinity, and it's a huge mess. But this is where the telescoping part comes in handy, because a telescoping series has a lot of cancellation, and we can see it right here between this e to the 1/2 in the first term and the e to the 1/2 in the second term. They have different signs, and so they end up canceling out. The same thing ends up being true for this e to the 1/3 here and the e to the 1/3 there. They have differing signs, and so they cancel out. And you can see that that pattern continues for this series, where the second part in every set of parentheses cancels out with the first part in the next set of parentheses. And so overall, we have a bunch of cancellation, and we can see that this e to the 1 over n term would cancel with the set of parentheses before it. And at the end of the day, the only things that don't cancel are the very first term and the very last term, because they don't have stuff to match with them. And so now that we have this much simpler expression for the nth partial sum, I can just take the limit as n goes to infinity of this term. And we already saw before that if I want to take the limit of this second term right here, then I can just use the fact that 1 over n plus 1 ends up going to 0 and plug that in up there because e is a continuous function. And so I end up getting that this is just e minus e to the 0, or in other words, e minus 1. And so we have now shown that this original series ends up equaling e minus 1. All right, now let's look at this next problem right here, where we have the sum from n equals 2 to infinity of 1 over n plus 2 times n plus 3. And so this one will end up being telescoping as well. There will be a lot of cancellation, but it doesn't look like it at first, because in the previous example, we saw that there was cancellation because there was a minus sign between terms, but this series doesn't have any negative signs, and so it might be hard to see that there should be any cancellation. However, from when we talked about integrals before, it turns out that there's a technique to rewrite the inside of this so that it does have two separate terms. And you might recognize that this is just a rational function, and so it'll help to use partial fractions here. And so the idea is that if we rewrite this sum as two different terms, then hopefully they'll partially cancel out with each other. And so I'll want to write 1 over n plus 2 times n plus 3 is equal to a over n plus 2 plus b over n plus 3. And as per usual at this point, I'll just cancel the denominators on both sides. And so I'll end up getting a 1 is equal to a times n plus 3 plus b times n plus 2. Now I can just plug in some convenient values. And when I plug in n is equal to minus 2, for example, then I get that a is equal to 1. Or if I plug in n is equal to minus 3, then I end up getting that 1 is equal to negative b, or in other words, b is equal to minus 1. And so now I can plug in this work that I've done for the partial fraction decomposition back into my original expression for the series. And I know that this series is the same now as 1 over n plus 2 minus 1 over n plus 3. And now we can see that there's this negative sign between the terms, and so it's likely that this will be a telescoping series. And so at this point, I just need to repeat the same procedure I did for the last problem, which is I want to sum up the first n terms in this series. I do have to be a little careful here because this series starts at n equals 2. And so that means that the first value I want to plug in is a 2 into here, which would give me a 1/4 minus a 1/5. Then the next term would end up being a 1/5 minus a 1/6. And then the next term would be a 1/6 minus 1/7. And then I'm going to keep on going until I have n terms total here. And so because I started with n equals 2 here, if I want n terms total, then the last thing I need to plug in is actually n plus 1. It doesn't really make a difference in the computation overall, but really if I want the nth partial sum, then this last term should be a 1 over n plus 3 minus a 1 over n plus 4, just so that there are n parentheses total. And then exactly like the previous problem, the second term in each set of parentheses cancels with the first term in the next one for all of these. And so I end up canceling everything except for the very first and the very last term. And so this ends up being 1/4 minus 1 over n plus 4. And if I take the limit as n goes to infinity of this expression, then I get the final answer for this series, which is just 1/4.